はい、ご紹介ありがとうございます。まずは、このような素敵な機会をいただいて、宮城市博士に大変感謝申し上げます。
ありがとうございます。
はい、僕は瀬川俊介という名前で、僕の研究は、Expanding your Bioimaging Toolbox with Quick and Fast Reactive Aggregation-Induced Emission Luminogens っていう内容で、宮城さんがおっしゃってくれたように、英語の方が楽なんで、英語で発表させていただきますが、質問とかは全然日本語で大丈夫ですので、お願いします。So before before going to my presentation, I want to use this opportunity for introduce myself. Again, my name is Shinsuke Segawa, and I'm PhD, no longer student in the Professor BenZhongTang group, and I'm also co-supervisor Professor Swan group for the Bioimaging facilities. And if I briefly introduce myself, I will say the polymer chemist and the chemical biologist. When I was undergraduate student, I joined the Professor Sivania group and Och group and in Kyoto University and Professor Ring group in University of Texas Austin for study the polymer synthesis. And after my master to PhD study, I changed my field to the chemical biology under the Professor Ursi group and Professor BenZhongTang group. So now I'm doing the mostly about the bioimaging, but maybe because of my polymer synthesis background, my recent work is mostly focusing on sorry, wait a moment. Uh, yeah, my recent work is mostly focusing on the polymolecular system for biological application. So mostly I'm focusing on the molecular aggregate system, how to use a molecular aggregate to the biological systems. So if I talk through my research in the very easy way, my research is a first probe synthesis and first imaging. So simply speaking, I make your molecule which show the emission, and using that molecule, I conduct your first imaging. And what is a first imaging? First imaging is the most direct way to visualize biological system in cell or in vivo. How does it work? Um, you have a biological sample, such as cell or animals, and inside the biological sample, always you have something you want to see. We call it a target of interest, TOI. And you prepare the molecule which show the emission and also which can target that TOI together. Those kind of molecules are called the fluorescence probes, and by externally adding those fluorescence probes, this probe will localizing the target, and you can see how target works by tracing their emission spectrums. And what's good point of those fluorescence imaging is it's very non-invasive, which means you can use a living samples. You can see the vivid behavior inside the biological system, and also fluorescence signals are very strong, so it can use with a high sensitivity. However, as I said, you need to, especially when you use a small molecular dye, you need to externally add a fluorescence probe from the outsider environment. So quality of the fluorescence imaging is directly the result of the quality of the fluorescence probes. So it is very important to make your good fluorescence probes. How? If I talk in the again simple way, the fluorescent probe can be designed by the connecting the flow port, which is a molecule which show the emission, and the function unit. Function unit might target the biological system or target a certain function group or control the emission of the flow ports. And by connecting those flow port and function unit, the flow port can target or control their functionality inside the biological system, and those flow port function conjugate can be considered as a first probes. Again, the flow port will represent the photophysical property of the fluorescence probes, such as brightness, photostability, and colors. And instead, a function unit will control a targeting activity, emission control behavior, biocompatibility of the fluorescent probes. And in my PhD study, I focusing the two properties. One is from the fluorescent flow port, and second is from the function unit. The one from the flow port, I focus in the aggregation-induced emission properties. And for the property from the function unit, I focus on the quick and Boltzmann reactivities. So what is aggregation-induced emission? We use AIE for abbreviation. AIE is a phenomenon which is discovered in our group in 2001. The conventional flower, like a normal flower with a planar structure, has a strong molecular interaction in the aggregate system, and they will quench your emission. But like our group has discovered that like AI molecules, or we call their AI gene, AI Luminogens, which has a twisted structure fluorescence molecule, can enhance the emission in the aggregate state because there's no like a known or weak molecular interaction in the aggregate state. So we call this phenomenon as a AIE, and their AI genes have their like a certain advantages compared to the conventional flowers. For example, the AID illumination can use in their very high working concentration. High working concentration means a higher emission signals. And also, like a AI illumination can be tolerant with the aggregation in the biological system. So their hydrophobic structures are accepted for to design the AI molecules, which is simply easier to make your molecules so that you can investigate more about what kind of AI illumination does work. And the most importantly, that it does enable the aggregate applications. AI illuminations has enabled using the molecular aggregate system in the biological systems. But however, there's a disadvantage as well. First, AI agent, I say that it can use for high working concentration and have the higher signals. But to be honest, emission strengths, emission quantum yield or absorbance will be very low compared to the planar molecules. So that to be honest, even you use a high working concentration, in many cases it doesn't have a better emission property compared to the conventional flower, which is usually in their direct solution. And even you say their hydrophobic structures are accepted. In the other sense, like a conventional flower can be used as long as you functionalize by their hydrophilic structures, hydrophilic functional groups. So this too is something that can be solved by the conventional flowers as well. So it's actually not very unique about their AI agents. And the most biggest disadvantages is first, the AI agents have the raw targeting properties. Because it has been aggregated, even you have a targeting unit in the molecules, the target unit will be get inside the aggregate and it cannot be targeted very well. And second, even their AI agent has enabled their aggregate applications. There's not many cases of their how aggregate that's advantages in the biological applications. So we really need to explore their how their what the advantages of their aggregate applications. So first, to solve the raw targeting properties of the aggregate, I consider I can use a strongest targeting, uh, targeting interaction between the two molecules. What it is a covalent bond formations. So if you functionalize the AI agents with a one functional group, we can form the bond formation with the biological molecules. That can be used as strongest way to targeting the biological molecules. And in that sense, I focus on the series of reaction, which is called the Crick reaction. Maybe I don't need to explain in this audience, but Crick reaction is one of the exceptionally simple reaction which form the no side products which undergo in the moderate reaction condition, and it's undergoing in the 100% yield, nearly 100% yield. So which is very useful in the biological systems. So in this concept, first, in my first chapter, I talk about the AI agent functionalized with a quick reactive function group, which is called the Enon group. Enon group can be react with amine and a silyl group in the quick manners. And indeed, using this a clickable AI agent, I have successfully conducted the bacterial imaging within the 2 to 5 minutes. However, I I didn't like this project so much because to be honest, this Enon group was super duper hard to apply for the many biological imaging system. So it can indeed image your bacteria, but because this Enon group can target most of the nucleophile in the biological system, if there's a other a biological component other than bacteria inside of those imaging system, it will target other biological component as well. So this labeling cannot be considered as a selective labeling at all. And moreover, maybe because this enone group will target everything in the bacteria, this reaction make the will kill the bacteria too much. Like it's a too toxic reaction. So in that sense, I had rather considered that we need a biosolinar reaction, not only the quick reaction. What is a biosolinar reaction? Biosolinar reaction, in very simple way of saying, like it is like a reaction, like quick reaction between the two abiotic functional group. Because these two functional group are abiotic, which doesn't exist in the biological system, um, it can very safely rebel any biological systems. And among the Balson reactions, I have focused on the tetragen ligation, shown here. The tetragen ligation is a quick reaction between the tetragen, the pole nitrogen embedded benzyl unit, and the strain alkyne group. And this reaction is very cool reaction because this reaction doesn't require the catalyst, and cell product is just a nitrogen, so it's not toxic at all. And these two triple bond and tetragen ligation is considered as one of the quickest quick reaction ever discovered. And this two component doesn't react with any other functional group. So it's very orthogonal, which means it's very selective and very fast. So in the concept, like end of the background study, like I focus on the making the compound the AI agent, which has a tetragen unit, and making this AI agent tetragen conjugate. I have focusing on the answer two questions. First, why do we need to use the AI agents? By showing the bioimaging tool only achievable by the aggregate emitters, only by the aggregate system. And second, why do you need to use a tetragen? By showing the bioimaging tools only achievable by the quick and Boltzmann reaction. In this concept, like I have focused on the first project, which is the aggregation strategy for designing highly fluorescent tetragen probes. So again, the interaction, like what I talk about the fluorescence imaging, which you prepare the biological sample and you add like a fluorescence probes to target your target. But to be honest, like in the many cases, that this target system doesn't work perfectly. Also, like a 90 something percent of dye will target the target of interest inside the cell. Some of dye will flow around those target, and like if this floating because of this floating molecule also had a very strong emission signals, that will give you the background signal, which result in the low contrast, bad resolution fluorescence images. How can we solve this background signal issue? There's a good way to solve this issue, which is called a photogenic imaging. What is photogenic imaging? Here you are. Like you prepare the molecule which show the non-emission, but if this non-emission molecule can turn on their emission upon their target recognition, which means because of this original molecule doesn't show their emission even floating around, so there's a no background emission, and as a result, you can get a high contrast imaging, which will result in the good fluorescence imaging result. So how can we design this non-emissive molecule which can turn on the emission upon the target recognition? There's actually the golden standard to design that kind of the photogenic probes, which is using of the emission quenchers. So you first prepare the normal fluorescent probe, which is like always turn on probe, which show the emission anytime, and you connect your quencher because emission quencher can literally quench your emission of the fluorescence probes. So this emission quencher complex will show non-emission. And if this emission quencher can be removed by the target recognition, which means the emission quencher will be removed, so the emission of those fluorescence molecule will be recovered. And as you can see, this latter process will act as a turn-on process, and which means the emission quencher and forward complex will consider as a fluorescent probes. And here, what is important is that because this turn-on efficiency, turn-on system is coming from the emission recovery from the normal emission quencher and forward conjugate. So turn on efficiency of this fluorescent probes is highly depends on the turn-on efficiency of the quenchers. So in this concept, first, strong quencher, and second, easy to remove quencher is very required. And this concept, actually, I was surprised to find it that tetragen does work as a easy to remove and strong emission quenchers. So again, tetragen can react with a strain alkyne group, which is called the bicyclonine, BCN, in the very quick chemistry way, which means they're easily react, very easy to react. And after the reaction with the tetragen and BCN compounds, tetragen moiety was removed. So first, it's easy to remove. And second, surprisingly, the mostly because of tetragen's n-pi stir transitions, tetragen can quench your emission of the fluoride, and as a result, tetragen does work as a very good emission quenchers. And to be fair, the tetragen fluoride conjugate type project probe is not my first idea. It has been discovered from the around 2010. And as you can see, there's a series of photogenic probes, which is designed by the connecting the fluoride with the tetragen units. But however, as you can see, the more the emission wavelengths get longer, because because the energy transfer efficiency of the tetragen fluoride will get lower, so the turn-on properties of the dot fluorogen probe will get lower. And if it's go to the red range, the emission turn-on is go to the just 4 times, which is not enough for the fluorogen imaging. So the researchers are very interested to the how to maximize the turn-on efficiency of the tetragen fluorogen probes, which means how to maximize the turn-on efficiency of the turn-off efficiency of the tetragen units. The previous study have focused on the design the single molecular system, which had a short fluoride tetragen distance. As you can see here, by putting the also substitution of the tetragen unit or using the amine linker, the tetragen and fluoride got a closer distance so that the emission quenching efficiency of the tetragen can be enhanced. However, those single molecular system is first hard to synthesize, and because that this is already the structure limitation, it will restrict the structure diversity. So I wanted to find a more general strategy to enhance or boost their tetragen's quenching efficiency. And here I have focused on the strategy which we named our aggregation strategy. How does it work? So it's just a simple system. I tune the hydrophobicity of the tetragen and the fluoride conjugate. So in the single molecules, the tetragen fluoride distance might be wrong, and basically there's only one distance between these two units. However, I consider if I make your fluoride and tetragen in the moderately hydrophobic, it will form the aggregate inside the water, and in the aggregate, tetragen and fluoride, this will have their multiple interaction, and it's because it's packed very well together, so the distance will be shorter, so the quenching efficiency of the tetragen will be boosted. And after that, if we put a triple bond group and remove the tetragen, I can get a turn on emission. And because the quenching state is a very dark, which means that will have their very strong turn on efficiency. However, if I consider about this strategy, there's a obvious limitation in using this system, which is aggregation cause quenching effect. What it is, as I say, the planar fluoride will have a strong pi-pi interaction in the aggregate system, and it doesn't show the good emission in the aggregate system. So it is very obvious that if you use a conventional fluoride, even after the tetragen is removed, it won't show the good emission in the aggregate system. So a dark state to dark state transfer, which means that it doesn't have a good emission turn on properties. So in that sense, again, I decided to use our AI agents, which had a very twisted structure, which showed a good emission properties in the aggregate state to achieve this strategy. So in this concept, I first prepared the tetragen AI agent conjugate, the 4 of the tetragen AI agent conjugate, and one a tetragen and planar di conjugate as a negative control. And all of those compounds has a good emission after the quick reaction. and it's covered from the violet to the nearly NIR range. And first, I wanted to check whether aggregate was reformed by those structures. And so I checked their DOS result. From the DOS result, we can see the nano-aggregate are formed by those molecules when it's dropped in the water. And what is exciting is this molecule show the emission quenching upon the aggregation. Upon adding the water, the emission intensity will be significantly dropped. And this emission quenching property will be observed in the other 4 molecules as well, and other 4 molecules as well. So to be noted, those spectrum is very agree because that this is tetragen Frober conjugate is already a dark state. So I'm checking the very negligible emission signals. And after I could observe the emission quenching enhancement upon the aggregation, I calculate the MD simulation. I conduct the MD simulation to check the Frober dye distance, Frober tetragen distance will become shorter or not upon the aggregation. So I conduct a single molecule MD and aggregate MD, and we could see that upon the aggregation, the tetragen dye distance is getting shorter. And what is more exciting is using the crystal structure as a model aggregate system. I conduct the TD-DFT calculation, and we could observe that in the single molecule system, the dark state is only coming from the n-pi stir transition in the tetragen moieties. But upon the aggregation, we can observe the other quenching system, which is coming from the dye to tetragen electron transfer dark state, and as well as the n-pi stir quenching state of the tetragen units, which means their dark state have been amplified upon the aggregations. And so indeed, we could observe that upon the aggregation, the emission quenching behavior of the tetragen got boosted. So next step is checking whether turn on phenomena will be observed or not. So we conducted this triple bond tetragen ligation as well, and check the aggregate emission of the post-Crick reaction compounds. And not surprisingly, if you use a non-AIGN planar Frober, because it doesn't show the good emission in the aggregate state, so that the turn-on efficiency of this planar dye tetragen molecules was not very good. Instead, if you use AIGNs as a Frober, because it has a strong aggregate emission, and upon the aggregation, it has a good dark state. So the turn-on efficiency of this molecule is very high, which leads to the 4,800. To be noted, this is one of the best value which is reported in terms of this phlogenicity of the tetragen dyes. And I checked the other 3 molecules as well. And as you can see here, 3 out of the tetragen AIGN conjugate shows a very good turn-on efficiency. Sorry, let me explain. This is a figure of the emission enhancement ratio for the y-axis and emission wavelengths as a x-axis. So which means if y-axis is higher, which has a higher turn-on emissions. And as you can see, 3 out of 4 AIGN tetragen conjugate showed a very good turn-on emission. And to be honest, one of them didn't show the good turn-on emission, but this is due to the other factor, which I will skip the explanation here. So in general, I can say that tetragen AIGN conjugate showed a very good turn-on emission in the aggregate state. So after I got a good turn-on emission, good photogenic system, I decided to use this for the biological imaging. I added this tetragen aggregate into the cell because it doesn't show the emission. It showed the non-emission in the aggregates. It doesn't show the emission in the system. But after adding the triple bond group, it showed a good emission inside the cell. And what's unique about this system is by controlling this triple bond localization, by changing this tail group of the triple bond group, you can target the different area in the cell, such as a mitochondria and cell membrane. You can see it's very regular membrane and the lipid droplet. And so far, I have successfully image up their mitochondria and lipid droplet and plasma membrane, and other organelles are under trial now. So in summary, I have made a system which can have an ultra high photogenic system by utilizing the aggregate formation, which means this ultra high turn on efficiency can be only achieved by the aggregate system. And here, I have discovered that upon the aggregation, there is an aggregation enhancing quenching system by the tetragen and the AI agents, the through space interactions. So the next step was that I consider if there's an intermolecular interaction between the tetragen and the AI agents, can I just keep connecting the AI agents and tetragen together? And how does it work? That is my second project, the co-aggregation as an exceptionally simple platform for preparing frozen tetragen pro with on-demand frozen searchings. So as I say, if you want to make your flowhole and tetragen conjugate, actually the synthesis is very hard. You need to prepare the flowhole and tetragen or tetragen precursors, and upon the quick reaction or whatever the reaction, you need to conjugate the tetragen and the flowhole, and that will work as a frogenic props. However, maybe you guys knows well that those flowholes in general need to make your pi extension reaction, which require heat, metal characters, and base. But to be honest, a tetragen unit is very degradable under the under the heat, or actually it's not degradable. It's very volatile under the heat, and it's work as a catalytic poison, and it's very unstable under the nucleophilic basis. So this reaction, this synthetic condition contradict too much, so which make your flowhole tetragen conjugate very hard to synthesize and very expensive as well. I consider whether I can skip this synthesis procedure by using the aggregate formation again. So this is the idea what I consider. Beforehand, you need to prepare the flowhole and tetragen, and using the organic reaction, you need to connect the tetragen and flowhole. But in my work, I consider if you can tune the aggregatability or hydrophobicity, more easy saying, of the flowhole and tetragen together, by just mixing in the water together, it may form the co-aggregate inside. And I consider that this co-aggregate might work as same as this covalently bonded tetragen flowhole conjugates. So in order to achieve this strategy, actually there's so many things to consider. First, I need to consider what kind of flowhole I'm gonna use. This point is very easy. We just need to use the aggregation-induced emission Luminogens, AI agents, because eventually we need to aggregate emission after the quick reaction. And second, we need to consider what kind of tetragen molecule are required to form the co-aggregate and show the good through space quenching result and good turn on emission as well. We have no idea, so we decided to synthesize a series of the tetragen molecules and check their quenching behavior first. So in this idea, we have prepared this much a tetragen compound with various side chains, such as a short to long alkyl chains and short to long pi conjugated system, charged pi conjugate systems. And by just mixing each other, very excitingly, some molecules show their emission quenching behavior. Which molecule show it? Actually, it was not very surprising that those hydrophobic tail group embedded tetragen compound show the good emission quenching behavior upon the coaggregation with AI agents. We confirmed that a coaggregation formation by the nanoparticle tracking analysis, and as a result, we could conclude that the long alkyl chain or highly pi conjugated system is important to form the co-aggregate, and co-aggregate formation is essential for emission quenching upon the mixing between tetragen molecules and the agents. And second step is checking the turn on behavior of this quench co-aggregates. So I check their emission turn on behavior. And this part was surprising as well. Among these four hydrophobic detergent molecules, this only three molecules showed a good turn on behavior. Instead, this one molecule showed a not good turn on behavior. Why? Because this molecule has a highly planar pi conjugated system. So even it have been co-aggregated with our AI agents, it will like stuck into the AI agents and it will quench emission of the AI agents. So in conclusion, we have discovered that like a long alkyl chain conjugated detergent compound or like a twisted pi conjugated pendant unit is important to achieve this co-aggregation strategy to get a detergent frozen improves. And after I gathered this result using one of this detergent molecules, I check whether I can quench and turn on the emission of any AI agents. So I just gathered so many AI agents in my research groups and check their emission turn off and turn on behavior. And very excitingly, in whatever color from the biored to NRR compound, upon the co-aggregation, that detergent compound can quench your emission. And upon the quick reaction, it can turn on the emission. And using this system, this turn on system indeed work in the cell system. Very excitingly, the turn on efficiency is very fast, which can turn on the emission within 40 seconds. And because of this turn on speed is very fast enough, I have proposed one bioimaging setup system, which is we named the temporal spectral separation. What it is. So in general, if there's a two molecule inside the process imaging system, if the two molecule has a different color of the emission, you can separate the signal between these two molecules, and you can check their you can conduct a multi-channel imaging, which means that you can target the one molecule location as well as other molecule location. But if this two molecule has a same color, which is impossible to separate their signal in the normal system because simply it has the same color. You cannot tell which one is which molecules, which color is which molecules. But using this turn on system, I have controlled the turn on time of these two different molecules. And by controlling the turn on time, even the color is same. Like I can separate those turn on two signal by changing the turn on time range. And using this system, I could successfully achieve the multi-channel imaging. In conclusion, I have achieved the exceptionally simple method for probe preparation by using this aggregate system as well. So I will skip this project because of time, and also this one is undisclosed project as well. So in general, in my PhD study, I have prepared the detergent AI agent conjugate, and I tried to answer the two questions: why AI agents and why biosimilar reactions. Why AI agents? I have achieved the ultra frozen system and the very simple preparation system, which is only achieved by the aggregate systems. And also, I have tried to answer the question of why detergent by showing the application of the detergent project probe, which is a flexible targeting of the multiple organelles and temporal spectral separation, which is enabled the multi-channel imaging using the same color dyes. That's all for my research, and I highly appreciate all Professor BenZhongTang and Professor Terence Wang, and my ex-supervisor, Professor Ochi Isonsibania, and Professor Motonari University and Professor Lin Nei for their training. Otherwise, their training, I couldn't achieve this PhD to achieve my PhD degree. And also, I appreciate all collaborator and supporters and all my friends in the Turn Scoop and Tan Scoop. Thank you very much for listening my presentation. That's all.
はい、ありがとうございます。
ありがとうご
じゃ
ざいます。
あ、質問ということで、じゃあ、張本お願いします。
いや、巧みな戦略でありがとうございました。プロジェクト1の時にちょっと僕がフォローできてなかったら申し訳ないですけど、クリック反応前からすでにその発酵オフの状態で凝集している証拠とかって 取れたりするんですかね。
クリック反応前に、それは細胞内でですか？
そうです、そうです、そうです。
細胞内でそれを捨てる証拠は、プロジェクト1では取れてないんですよ。全く取れてないんですけども、同じ条件で、プロジェクト 2で、エミッションがクエンチしてるので、
なるほど。
そのプロジェクト2だったら、エミッションがクエンチしてなかったら、ごめんなさい。凝集してなかったらエミッションがクエンチしないので、エミッションがクエンチしてるってことは凝集してるんだなっていう考え方。
なるほど、なるほど。ありがとうございます。
はい、ありがとうございます。じゃあちょっと自分から質問なんですけど、最初のプロジェクト1で、TPE が上がってターンオンするときに、ちょっと超波長に発光がある気がするんですけど、あれは何由来の発光
TPE を、
今あった。
どれですか？これですか？
いや、もっと先の、これですね。これ、
黒
黒のビフォークリックの、クリックの前ですね。
これですか？
これが何由
これ
来の発光？
が、多分こっち見たら分かりやすいんですけど、答えから言うと、テトラジンのローカルエキサイテーションですね。結局、凝集して、エナジートランスファー効率が上がって、行く場所がテトラジンの N パイスター繊維なんで、
そこから光るときは。
テトラジン N パイスター繊維が逆にエンハンスされてるって考え方も、できなくはないっていう考え方です。
量子率は低いけど、クエンチしたときに見えちゃうというか。
そうですね。あと、言ったら AI と同じ考え方で、凝集状態ではクエンチングパスウェイが減るので、ちょっと、そのダークステートであっても少しエミッションがエンハンスされるっていうことが起こります。
なるほど、確かにエンハンスされてるですね。なるほど、なるほど。あと、クリックした後の、なんか2個アゾの、やつ、構造あると思うんですけど、これはクエンチしないんですか？
それすごくいい質問で、それがここの問題なんですよ。見たら分かるように、これ、黒いドットが今までのワークなんですけど、ここら辺で高いターンオン効率がなくなってるんですよね。これは、そのクリック後のやつもクエンチをする。
なるほど、なるほど。
短波長だったらクエンチをしてしまうっていうことが起こってるから、
これ以上だと、そっちにエネルギー移動そもそもしないから大丈夫だけど、これ以下だと、
そうなんですよ。エネルギー移動が起こってしまって、そのピリラジン、N が2つあるユニット由来のクエンチングステートに行ってしまうと。
なるほど。
実際それは TDDFT 計算で調べられてます。
逆にその超波長に行くと、もうそもそもテトラジンにも同じような現象が起こっちゃってっていうふうなこと
そうなんですよ。なんで、ここがこう、どんどん、
なるほど。そこはもう結構。
クエンチングエフィシェンシーが下がって、ターンオンエフィシェンシーも下がるんですけど、テトラジンのちょっといいところは、すごい電子不足なんで、距離さえ縮めて、あと、配合さえうまくやれば、今度は CT タイプ、エレクトロントランスファータイプのクエンチングパスウェイが出てくるんですよ。なんで、そのエナジートランスファーだけじゃないクエンチングがテトラジンでは可能なんで、その超波長でも、テトラジン自体のその N パース耐繊維は600くらいにしかないんですけど、それ以上にいってもちゃんとクエンチができる。
なるほど、なるほど。ありがとうございます。他に質問する人いれば、ぜひお願いします。あと、俺から、多分あんま、本質的じゃないんだけど、なんだっけ、パーティクルカウントのところで、最後の方。
何のパーティクルチャッカーのやつかな？
今の。そう。これなんかめちゃくちゃ振動してる感じのデータになってるの、これなんか理由があるんですか？これ単純に俺やったことなくて。
ここはサチってますね。サチってるからちょっと振動してます。
サチって。いや、なんかそのちょうどいいサイズのところってなんかパパって出てるな、これなんで。
これ、どこですか？
右の、TPATZ の、なんかこう、多分そう。
これは、なんかサチったらこれが起こるんですよね。なんで、
サチるっていうのは、どういうサチリ？
ナノパーティクルトラックアナリシスが、言ったらサンプルを軽いセルにこう通して、カメラでパシャって撮ってる感じなんですよ。カメラでカウントしてるんですよね。で、ただ、量が多くなったら、その2つのシグナルが、
かぶると。
かぶるようになって、カウントがすごい下がっちゃうんですよ。なんで、これぐらいだったら分かるんですけど、ここまでいったら、サチってしまう。
これ薄くしたら測れるっていうふうな感じ？
凝集状態がその濃度依存になっちゃうんで。
そっか、確かに。しかもこれイオニックだと。
薄くしたら測れるんですけど、
そうすると
凝集してないっていう理論をするのが、ちょっとずるくなっちゃうっていう。
なるほど。 それはもう結構、なんか装置的な問題ってことですね。
なんか DLS とかでも似た話になっちゃいます。
うん。
一応、なんか DLS じゃなくてナノパーティクルを使ってるのは、この写真が撮れるからで、まあ、なんか察知ってても、ちゃんと、写真があるから、まあ、業種はしてるでしょっていうのが分かる。
ああ、なるほど、なるほど。ありがとうございます。あと、何だっけ。そう、なんかアグリゲーションを起こしたときに、結構なんだろう、違う、なんていう、反応点と一緒に混ぜて、表面収縮ライクなことをする研究ってあると思うんですけど、これはそれはできるんですか？
ごめん、もう一回言っていただけますか？
いや、いや、全然、色素とか凝縮させて、なんか
はい、
ナノパーティクルの、
はい
フロージェにするときに、
はい
なんか反応性の置換機とかを、強凝縮みたいなのさせると、例えばそのチオール表面に生やしたりとか、なんかいろいろできると思うんだけど、今回のプロジェクト1でも2でもいいと思うんだけど、なんかそういう、なんか表面の収縮みたいなのできるんかなっていう。
今、多分、ナノパーティクルの話してる？
ナノパーティクルの話。はい。
ナノパーティクルで、これだと、表面がどの分子になるか、表面にどの分子が出るかがちょっと気になってないです。ただまあ、一応クリック反応が起こってるので、テトラジンが表面に出てて、そこからターゲット脳があるっていうのは、ちゃんとできてます。
そう、だからターゲッティングユニットそもそも混ぜればどうなるんだろうと思って。ターゲッティングのなんかユニット、このなんかアルキンがないやつを、そもそも混ぜ込んで凝集させたらどうなるんだろうっていう。
ターゲッティングのないやつを混ぜ込んで凝集
ターゲットのその認識する分野と、あと BCN があると思うんだけど、BCN がないターゲッティングのやつ
を、BCN がないターゲッティングのやつを凝集させた。
なんか何つけてもいいんだけど、そう、強凝集できるようなやつにすれば。
それはもう、僕の論文バージョンのこのプロジェクト2のイントロですね、基本的には。感覚的には、そのテトラジンが、今回のターゲティングユニットっていうイメージで、ディスカッションでは一応別に他のファンクションユニットでもできるんじゃないかっていうスコープを話してます。
なるほど。
で、まあ、そのアイデアはすごく面白くて、面白いんですけど、時間があればやりたかったんですけど、
なるほど。とりあえずはテトラジン。
とりあえずはテトラジンからっていう考え方ですね。
あと、YouTube からで、細胞内小器官ターゲットの、化合物の波長漏れ込みとかはどうでしょうかっていう。
波長漏れ込み、それはこの2つの色素のってことですよね。
ちょっとこれ波長漏れ込みっていうのが。
多分、こうローカライゼーションしてて、この2つの波長をかぶってないかだと思うんですけど、それは同じ条件で色素を使ってないやつを使って盛り込みがないことは確認してます。
なるほど。これだからクロストークっていうか、相互作用
がないっていうのクロストークを取ってしまってないかっていう意味だったら、それは一応考慮してします。
なるほど、ありがとうございます。他ありますか？なければ、大体時間。じゃあ、張本お願いします。
これ、混ぜ込むっていうメソドロジーは、原理的にはAI イージェンとかにレセプターをつければ、極材性とかもいずれ制御できるようになってくるっていうことなんですよね。
AI イージェンにレセプターをつけれ
ば、なんかここだけに取り込ませるみたいな感じで、組織とかそういうところでもっと、
その AI イージェンにとレセプターを共有して
AI イージェンにレセプターつけとけば、細胞か組織のここに
そういうことですみたいな。それはできるんじゃないですかね。できる気がします。なんなら結構そういうのはよくあるのはフォリックアシッドをつけて、がん細胞をターゲットのフォリックアシッドリセプターに行くようにするとかは結構よく使われる戦略なんで、ただ協業種でやってる人はあんまりいないですけど、基本的にはナノパーティクル作るんですけど、
なるほど。
協業種で実際分解してないっていうのが今回の研究で分かったので、意外とできるんじゃないかなっていうのが。ただ、インビボのアニマルの動的なシステムに入れてしまったら、いずれ分離しちゃうかもしれないです。
なるほど。
わかりました。そういうレベルではいける気がします。
あと、なんか追加、さっきの質問、学さんからなんですけど、その他よく核染色とかの漏れ込みとかをきちんとチェックされてるとすると素晴らしい。これはコメントですね。
ありがとうございます。
で、ヘキ素染色とかですねって言ってたんだけど、ヘキ素染色って何ですか？俺の質問なんだけど、これ。
ヘキ素染色は核の。
なるほど。
これは ですよね。
いや、わかんない。
ホーチェスと一緒、ホーチェスと一緒ですよね。ごめんなさい、ちょっと。
いや、わかんない。多分なんか
日本語がわかんない。
コメント。
ホーチェスと同じ話なら、フィクスと多分合ってると思います。その核染色で、まあ、基本的には核染色した方が細胞を見やすいんで、やるべきなんですけど、ちょっと AI 人って波長がどうしても広くて、漏れ込みが激しいんで、できる限り、
いろいろ混ぜたくない。
いろいろ混ぜたくないっていうの
なるほど、
があって、
なるほど。
ちょっとサボっちゃってますね、ヘキスト。
なるほど、なるほど。いや、ありがとうございます。はい、じゃあ、時間なんで、終わりにしたいと思います。ありがとうございます。
ありがとうございます。